Hey there, this is the first video all about sequences. And sequences are all about patterns. We see patterns all the time in math, and now it's time to put some structure into what we're going to see as far as our patterns, because it'll lead to some great things down the road. So let's take a look and see what we got here. In this particular video, we've got 3 level 1 examples and 1 level 4 or level 2 example, which is number 4. So keep watching. These are actually go really quick as far as the problems go. But let's get some introduction here. So a sequence is just some sort of an ordered list of numbers, and each of our numbers we call a term in our sequence. So we could have a finite sequence, which is just a finite number of terms, like 4, 5, 6, 7 is a sequence, and there are 4 terms there. Or we can have an infinite sequence, which actually we're going to work with a lot more often in this class. So as an infinite number of terms, so we can have like 4, 8, 12, and then we draw these ellipses, these 3 dots right here to show that that we just keep on going with our sequence. Sequences can also be written in what are called explicit formulas, where the nth term is some sort of function of n, or what we call a recursive formula, where we figure out future terms based on previous terms. Right? And recursion is something that you'll see later on if you ever do anything with computer science down the road. So let's just dive right in and let's see a couple of examples here. Find the next 4 terms of the sequence 19, 15, 11, and 7. So if you ever played any puzzles, this is just about like finding patterns in puzzles and all that sort of stuff. So one thing that hopefully you notice is a possible pattern is that we're subtracting by 4 each time. Right? So if we apply the pattern, what we can say is our first term, we usually write that as a sub 1 is 19. Our next term, a sub 2 is 15. A sub 3 is 11, and a sub 4 is 7. And this is a little subscript right here, which is why we call it sub 4. Right? So our pattern is that we're subtracting by 4 each time to get the next term. So we would say a sub 5 is the previous term, 7 minus 4, which is equal to 3. A sub 6, we subtract another 4 to get negative 1. A sub 7, we get negative 5, and we subtract another 4. And a sub 8, we get negative 9. Right? So this is all about trying to find patterns, and some of them work a little bit better than others. This, in fact, is what's called an arithmetic sequence, which we get by a common difference between each of these terms. If you were to subtract each consecutive term, you get the same number, which is 4. All right, find the first 4 terms of the sequence given by a sub n equals n squared times negative 1 raised to the n. You're going to see a lot of this negative 1 raised to the n part right here. All right, and basically what that does is it helps us to alternate between positive and negative numbers. So you're given a formula. Now can you actually figure out the terms? Well, a sub 1, we plug in 1 for n, the first term, and we get 1 squared times negative 1 to the first, which is negative 1. A sub 2, we plug in 2 for n, 2 squared times negative 1 squared is equal to 4. I do the same for 3 and 4, and I get negative 9 and 16. So notice what we've done with this negative 1 to the n, it's allowed us to alternate between a negative and a positive number. And we're doing so with all of our squared numbers here. Okay, so this sequence that we just saw right here is what's called an explicit formula for a sequence. And basically what it means is we know how to find a sub n if we just know what n is. And we just plug it into some sort of a formula where it's direct. We figure out right away what our value is. It was pretty easy, actually. A recursively defined sequence is one where we try to figure out what our term is based on previous terms. So you'll see something in a recursive sequence that looks like this, where you have a first term, a sub 1 is equal to 5, and then it tells you how to write the next terms beyond that. So this is saying a sub n is equal to a sub n minus 1 plus n minus 4. Well, a sub n minus 1 is the term before a sub n. That's what the n minus 1 part tells us. So what it's saying is take the previous term, add it to n, and subtract 4, and you get your new term. Let's see an example. If n is equal to 2, I plug in 2 right here for n, so it says a sub 2 is equal to a sub 2 minus 1 plus 2 for n minus 4. And if we simplify that a little bit, it's telling us our next term, a sub 2, is a sub 1 minus 2. In other words, it's the previous term minus 2. So we see that nice formula right here. When you see n minus 1, that's referring to your previous term. Well, when we plug in 5, which was our a sub 1 term, we get 5 minus 2 is equal to 3. If I want the third term, I do the same thing. I say n is equal to 3. A sub n minus 1 is a sub 2. n is 3, and then minus 4. So a sub 2, we go back and we say, well, what's the second term? That's 3, so I plug that in. And then I add 3 and subtract 4, and I get negative 4. N equal to 4. You kind of get the picture, hopefully, right? The fourth term is the third term, plus 4 minus 4. Where's the plus 4 coming from? Well, that's what n is, right? So a sub 3 is negative 4, so we plug that in. Negative 4 plus 4 minus 4 is negative 4. So we keep on using the previous term to find our next term. And that leaves us finally with n equal to 5, our fifth term here. So it's the fourth term plus 5 minus 4, which is equal to negative 3 when we plug in everything. So that's what we call a recursively defined sequence. So sequences are everywhere. I'll give you an example right here of plants. And growing plants have stems that grow for a second month before supporting branches. At the end of the second month, it sprouts a new branch and continues to sprout one branch that's new each month. If this pattern continues, how many branches will the plant have after 12 months? All right, so here's the idea, right? All right, so I wrote it out right here. Our first month, we just have the one branch. Second month, we have one branch still, and it takes until the end of the second month to actually sprout a new branch. When we get to month number 3, now we have two branches. We have the first branch and the second branch. And it works a little something like this, right? So when we have the fourth month, that first branch is sprouting a new one, but the second one that was formed in month 3 is still too young. It doesn't actually form a new branch yet. So we only have one extra branch. But when we get to month number 5, both the first and the second branch are now sprouting because it's been 2 months for both of them. So now we're up to 5. And then in the 6th month, we have now a third branch that comes up from the one that came up in the 4th month. Right? And we keep on growing, and the number of branches increases in this way. And maybe you're familiar with this. This is what we call our Fibonacci sequence, right? The numbers 1, 1, 2, 3, 5, and so on. And the pattern is basically, all right, this is just kind of repeating here. In months 1 and 2, we have one branch. All right, in month 3, we have two branches plus the stem, original stem, plus the new branch that we have. All right, in month 4, we have 3 branches. All right, the stem. Month 3 has a new one, and month 4 has a new one. We have 5 branches in month 5. Those were alive in month 4, and then a new one from month 3. And we're continuing to add on as we go along. So there's a pattern to all this. So our formula is what we call the Fibonacci sequence. And basically the idea is what we're doing is we have our first term is 1, which is the stem. Our second term is also 1, still just the stem. And then to get all of our new branches, right, we take our previous 2 months and add up the number of branches we had in each of those months, if you can see the pattern in here. So this is a famous sequence called the Fibonacci sequence, right? And it's often seen in situations where we've got some sort of growth like this situation. All right, last example here. So we want to find a recursive formula for the following sequence: 6, 24, 96, 384. So I want you to pause maybe for a second. Try to think about what you're noticing about these numbers here. What are we doing to get the next number? Well, if you said that we're multiplying by 4, you're right. So for a recursive formula, we need an initial term and a formula for getting the next term. Well, our first term, our initial term, is 6. We'll call that a sub 1. How do we get the next term? Well, we just said it. We multiply our previous term by 4. So the recursive sequence has the first term, a sub 1 is equal to 6, and our next term, a sub n, is 4 times the previous term. That's a sub n minus 1. Right? And we've got ourselves a recursive formula. Well, we can do the same with an explicit formula. For an explicit formula, we need to be able to find out a sub n if we know what n is. We don't have to go back and look at previous terms for that. So if we multiply by the same number each time, maybe you've seen this before in an algebra class, that's the same as an exponent. 4 to the n means 4 times 4 times 4 times 4 times 4 n times. All right, so that's what we call an exponential model, and we'll explore more of this later on because this is what's called a geometric sequence. And a geometric sequence, when you go to graph it, looks just like an exponential model because you're multiplying by the same thing to get the next term. So in summary, sequences are fantastic. I love them. They're very useful, but you got to be able to recognize the pattern, and we'll get some practice in class. Explicit formulas give the nth term as a function of n, while recursive formulas define our terms that follow our first terms in terms of any previous terms. So we're using our previous terms to find our next terms. Thank you so much. We'll see you in the next video.